Now we get to enjoy his talk.
Yeah, thank you, everyone. First of all, I would like to thank Christians for providing me a chance to talk in these seminars. And today I'm going to talk about the gravitational waves and the neutrino emission from compact binding mergers. And I would like to introduce our latest research based on the numerical relativity simulations. And I am Kenta Kiuchi from Yukawa Institute for Cellular Physics in Kyoto University. And today's talk is based on the work in collaboration with the Kotaro Kyudo, Yuichiro Sekiguchi, Kenta Kiuchi, Masaru Shibata, and the new one. And this work is supported by the high-performance computing infrastructure in Japan. And this Chinese character is pronounced as K, which is the name of the 10 petaflops computer in Japan. And this is a talk plan. And first of all, I would like to give introductions. In particular, I'm going to talk current status of numerical relativities, because some of you might not be familiar with it. Then, in second part, I'm going to talk about the binary Newton-Star merger simulations in numerical relativities, mainly based on our research. Then move on to the black hole Newton-Star mergers. And finally, I summarize the talk. Okay, let's start from introductions. Our research target is high energy astrophysical phenomena, such as compact binding mergers composed of black hole reducers, or supernovae, or black hole formation by massive stellar collapse. In such phenomena, all the basic interactions must play an essential role, because the general relativity is required to describe a strong gravitational field around the neutron stars and black holes, and the nuclear matter is described by the strong interactions, because the typical density is well beyond the nuclear saturation densities. Because of the hot temperatures and high density state, the weak interaction is indispensable for the neutrino emissions. And the magnetic field would play an important role, because it is observationally established that the neutron stars have a strong magnetic field whose strength from 10 to 11 to the 10 to the 14 times. And this research target has highly time-dependent features. So you need numerical modeling to theoretically investigate them. So the aim of the numerical relativity is to figure out the high energy astrophysical phenomena in which all the basic interactions should be implemented in self-consistent way in numerical simulations. So let me explain how you implement all the interaction in self-consistent way. The first basic equation is the Einstein equation, which describes the evolution of the metric G mu, and the equation of motion of the fluid, and the radiation field, and electromagnetic field, as well as the number current is derived from the conservation laws. In the fluid case, we know that the equation of state gives you excellent, nice closure relation, and this functional form is derived from the nuclear theories. Next, let me give a brief review of the history of the numerical relativity. This is a chronology of the numerical relativity, and numerical relativity has begun around the 60s. It was thought that the 3+1 decomposition formulated by Arnold, Deser, and Misner was useful for the numerical simulations, but some numerical experiments showed that the simulations were crashed due to the constraint violations. Nakamura and Shibata had proposed the reformulations of the AEM formalism, in which a spatial derivative of the metric was introduced as a new variable to rewrite the evolution equation. The Baumgarten and Shapiro have proposed a formulation which is essentially saying essentially same as both by the Shibata and Nakamura. And today, this formulation is called as bound gravitational field Shibata-Nakamura formulation. And this is one of the standard formulations in relativities. Although the BSSM formulation works well in the absence of the black hole, it was a long-standing problem to do long-term simulations for the black hole finding models. In 2005, there were two breakthroughs. The first one, one was done by Franz Pretorius, and the other was done by two independent research groups. The former implement excision technique inside a black hole, and the later is based on the BSSM formulations. And there are no principal difficulties to solve the Einstein equations based. Note that the development of gauge condition, which is suitable for the numerical simulations, and the construction of initial realistic initial condition is the important ingredient as well. The left-hand side of the Einstein equation is okay. So the next task is the right-hand side of the Einstein equations. In general relativistic hydrodynamics, the numerical scheme to capture a shock is required because it contains a discontinuity of physical quantities. And on the other hand, the finite difference scheme is based on the Taylor experiments. The numerical relativity group in Valencia and in the Valencia University and Max Planck Institute for Astrophysics have implemented the numerical scheme, which was originally developed in non-relativistic hydrodynamics. So it is now possible to capture a shock with high accuracies. And there is a problem inherent to relativistic hydrodynamics, which is sometimes called a primitive recovery. Because the high-resolution shock capturing scheme is based on the conservation laws, not the less mass density, but the Lorentz factor weighted less mass density is used as a basic variable. The things is same in the momentum, which is weighted by the specific enthalpies, and the energy density is composed of the enthalpy Lorentz factor and so on. The Lorentz factor is obtained from the three spatial components of the four velocities, and the specific internal energy, which is included in the specific enthalpy, should follow the first law of the dynamics. This means that you should find the Lorentz factor and the specific enthalpy simultaneously, and this leads to a non-linearly defined dynamics. If you use the tabulated equation of state, this procedure becomes more messy. The extension to the general relativistic magnetic hydrodynamics is straightforward, and it has been formulated by the Shibata and Kiuchi and Dew and his collaborator in 2005. Since then, it is feasible to do GL-MHD simulations in the framework of the ideal MHD. The extension to the GL resistive MHD has been proposed recently by them. The next step is radiation field for the neutrinos. The first general relativistic leakage simulation has been done by my collaborator Kyoto Kiuchi. In his formalism, it starts from the conservation laws, because the total stress energy tensor should obey the conservation law. The fluid and the radiation field interact through the source term Q. Here it is assumed that the radiation field energy tensor is divided into the trapped neutrino part and the stream neutrino part, and later interacts through the leakage source term. The trapped part is combined with the fluid source term, and what you have to do is to solve these two equation equations. The leakage term is evaluated by the diffusion rate and the local reaction rate, which are weighted by the optical depth. A step toward more sophisticated radiation hydrodynamics has been formulated by us, in which is a variant formulation based on the Boltzmann equation. In this formalism, zeros and first order momentum of the distribution function are the basic variables, and the second momentum is obtained by the closure relation, which connect the neutrino thick region to the thin regions. Since 2011, it is feasible to do numerical relations with microphysics as well as the neutrino cooling. The last thing is a little bit technical issues. The target of the numerical relativity had a large dynamical range in general. For instance, in compact binary mergers, the typical size of the neutron stars or stellar mass black hole is on an order of 10 kilometers. On the other hand, a gravitational wave length is several hundred kilometers. So you have to cover the neutron stars, black hole, and gravitational waves simultaneously. To conquer this problem, our group implemented two kinds of mesh refinement technique. The left-hand side is a nested grid method, in which all the grid have common origin. The right-hand side figure is a moving box or adaptive mesh refinement technique, in which the neutron stars or black hole is covered by a small grid and a small box, and these boxes around each other. And this is a recipe for the numerical relativities, and the blue-colored region is a main part, in which the Einstein equations, matter equation, as well as the grid condition are solved in cyclic manner. Today, I mainly focus on the compact binary composed of the neutron stars and black holes. The main motivation of this research is gravitational waves, of course, because the Japanese gravitational wave detector KAGRA and advanced LIGO in USA and advanced VIRGO in Italy will start observation within a few years, and the coalescence of compact binary merger is one of the most promising sources of the gravitational waves. So if you detected gravitational wave from them, they could tell us the validity of general relativity in strong gravitational field, the equation of state of high density matters, and they may give a constraint or they may give information for the central engine of the short hard gamma burst. Motivated by this part, the researcher in this field are now seriously discussing what the electromagnetic counterpart of compact binary merger is, apart from the hypothesis that the central short hard gamma burst is driven by the compact binary mergers. There are two conservative scenarios. The first one is proposed by the Naka and Grant, and they discussed ejected matter during the merger process interact with the interstellar medium, then an electromagnetic signal is emitted by the synchrotron radiation. The other scenario is a radioactive decay of the hard process element in the ejected matters. To assess these scenarios, we should verify the properties of the ejected matter, such as mass, velocities, and the chemical composition, and so on. In the first part, I would like to introduce the binary neutron merger case. There is plenty of numerical relativity simulations of binary neutron stars done so far, and they have revealed that the evolution of the binary neutron star exhibits diversities. If the total mass is greater than the maximum mass with constant k, the binary collapses to a black hole immediately after the merger. This is a density contour on the orbital plane, and the bottom figure is the gravitational waves emitted in each epoch. If the separation between the two is very large, they are nicely approximated by the test particles, and the gravitational wave in this phase is a sinusoidal wave with increasing the frequency and increasing the amplitude. Once the star gets close, tidal deformation neutron stars makes a deviation from this particle. After the merger, the star collapses to a black hole because he cannot sustain his weight. And we call this path as a type 1. And after the mergers, after the black hole formation, the gravitational wave is characterized by the quasi-normal mode of the black hole. If the mass is not so large, a massive neutron star will be formed as a remnant. This star has a mass greater than the maximum mass of spherical neutron stars because of the rapid rotation and thermal pressures. This is a figure for the snapshot of the density contour and the gravitational waves. And before the merger, the things is the same as a type 1 case, and the difference appears after the formation of massive neutron stars. Because these massive neutron stars gradually contract because the gravitational waves carry away the angular momentum from the system. And the lifetime of this massive neutron star strongly depends on the total mass and the structures of the gravitational waves, structure of the massive stars. So we categorize the type 2 as a short-lived massive neutron stars and type 3 as a long-lived massive neutron stars. We found in our numerical simulation that the constant of K is given in this range, and note that the larger for the maximum mass or the smaller the total mass, the binary evolution, binary will take a right-hand side evolution mass.
So how does K depend on the equation of state that is being used?
In this work, we adopted 5 kind of equation of state, and like APL and H4 and SLY, and values from 1.4.
Okay, so this range covers the range of different equations of state.
Right. Okay, there are 9 binary neutron stars observed so far, and this table shows the mass of the neutron stars. And because the canonical mass of the neutron star is 1.35 over 1.4 solar mass, and the mass ratio is likely to be less asymmetric, the canonical total mass is thought to be 2.7 or 2.8 solar mass. On the other hand, the observation of this pulsar gives a constraint on the maximum mass of the spherical neutron stars, and combining these facts with our findings predicted that the right-hand side evolution is more realistic path.
But the 1.97 solar masses, this is just the lower limit on the maximum mass, right? The theory, the nuclear equation of state says something like between 2 and 3 solar masses.
So what I want to say is that this case might be a rare case. So how can you distinguish these evolutional process by gravitational wave observations? Let me consider type 1, which is upon the black hole formation case as a first example. This is again this plot is again the binary neutron stars. The evolution of type 1 case, and the right-hand side figure is a schematic picture of the gravitational wave spectrum. And because the frequency increases with shrinking the orbital separation, this direction is evolution directions. The quadrupole formula together with the test particle approximations predicted that the spectrum is proportional to the frequency with power index being -1.6. In type 1 case, the spectrum starts dump exponentially at some point, and we call this frequency, which characterizes exponential decay, as a cut frequency. And there appears a hump in the high frequency side. This cut frequency imprints a point where the binary loses, the system loses the binary shapes. Because as you know, the gravitational wave is efficiently emitted if the system has a binary shapes. And the system loses the binary shape depend on the radius of the neutrons. That means the cut frequency brings the information of the radius of the neutron stars. We confirm this by performing a systematic studies for total mass and mass ratios and the nuclear fusion of state. The bottom figure is a cut frequency as a function of the compactness of the neutron stars, in which we vary the total mass and mass ratio and the fusion state. And you can find a very clear correlation between the two. So the strategy to constrain the equation of state is as follows. First, by analyzing the in-spiral waveforms, you can obtain the mass and the total mass and mass ratio of the system. And then, by analyzing the merger waveforms, you could determine the cut frequencies. And using the relation found in these studies, you can infer the mass of the radius, so you can reconstruct the mass and radius relation observation. Let's move on to the type 2 or type 3 case. As I said before, in this case, massive neutron star is born after the mergers, and this massive neutron star emits the gravitational wave periodically. If you look at that in the Fourier space, there appears a peak around several hundred kilohertz. And this peak frequencies imprint the information of the internal structure of the massive neutron stars. So if you detected this peak, you can obtain the information of the radius of the neutron stars. We explore this problem in the two directions. And one direction is use the nuclear theory-based zero temperature equation of state, adding the thermal pressures, which is a sort of parametric study. And the other is that we use a finite temperature equation of state together with neutron cooling. This is a result for the 1.25 solar mass and 1.45 solar mass, in which the neutron star is modeled by the chain equation of state. On the left-hand side figure is a density, and the right-hand side figure is an entropy on the orbital plane. Let me show again. After studying the simulation, the separation between the two gradually decreases due to the radiation reaction. Then the less massive neutron star is tidally deformed. And tidally elongated less massive neutron star forms a satellite around the massive neutron star's core, and then massive neutron star remnant is formed, which shows violent oscillations. The typical maximum density is greater than 10 to 15 grams per cubic centimeters, and the maximum mass is greater than 10 in the unit of the Wilson.
So which equation of state is this?
Shen.
This is with the Shen.
Yeah, Shen equation.
Okay.
This animation is an animation for the neutrino emissivities and the electron fluxions. We prepare the plane which is perpendicular to the orbital planes. And you can see that the intense neutrino emission close to the pole. This intense neutrino emission is result in the high amplitude neutrino luminosities, which is about 10 to the 15 ergs per second. The animation of the electron fluxion shows that the ejected matters in this, from this massive neutron star has relatively low electron fluxions, which is important to discuss the R process in binary neutron star merger.
Why is the electron fraction along the pole very high?
Yeah, but I think this in atmosphere we assume the electron fraction is 0.5, and
Well, the
this,
density is just very low.
yeah.
Okay.
So the neutrino emission is not very beamed, it's more isotropic.
Yeah, no.
Actually, it looks, I can't tell from the, it's more along the equator than the poles that the neutrino is emission.
And in this simulation, we use a very simplified closure relation. So for the radiation field, so I mean the direction of neutrino cannot be estimated in these simulations.
So at the lowest order, it's isotropic. But you don't have any magnetic fields yet.
Yeah.
And the spins are very important there.
Spin has
Of individual neutron star spins.
no spin, the rotational case. So let me show the gravitational waves and the time of evolution of gravitational wave frequency for the Shen 1.2 and 1.5 solar mass case. And as expected, the massive neutrons, remnant neutron stars becomes strong gravitational wave emitters, and this oscillation is related to the fundamental mode oscillations of the neutron stars. And the amplitude gradually decreases because the gravitational wave carry away angular momentum, and the hydrodynamical interaction proceeds angular momentum transfers. So the star gradually approaches nearly asymmetric structures. And the gravitational wave frequency in the massive remnant neutron star phase approaches to asymptotical values. So what about the other models? In these models, we vary the equation of state, the total mass and mass ratios, and you can see that gravitational waves show diversities. And in particular, the gravitational wave frequency strongly depend on the stellar models, and there are some trend in the gravitational wave frequencies. And it is well known that the soft equation of state result in more compact neutron stars, which leads to higher gravitational wave frequencies, because the gravitational wave is emitted by the fundamental oscillations of the neutron stars, and the frequency of the fundamental mode is proportional to the inverse of the average dynamical time scale.
And the duration?
Third,
And the duration of this?
duration.
So-
Duration is also depend on the models.
And since I can't tell, I guess you're cutting everything off 30 milliseconds. Do any of them last like a long time?
This one?
Like seconds? Do any of them last seconds?
Yeah. In this case, lifetime of this massive neutron star is determined by the neutrino cooling time scale, which is estimated as 1 or 2 seconds.
So what equation of state did you use there? I can't read this.
Okay, this case APL, and this is ALF, and this is all of this is parameterized piecewise polynomial.
Also, there's no neutrinos.
In this case. So Barsfine and Yanka have found in the simulation that the peak frequency has a tight connection to the radius of the neutron star with 1.34 mass, 5 solar mass. So we made a plot of the peak frequency as a function of the radius of 1.8 solar mass. And we found a strong correlation between the two. However, our finding relation has some shows small dispersion, and it is not as high as tight as found in the Barsfine and Yanka. The strategy to constrain the equation of state is as follows. And by analyzing the in-spiral waveforms, you can obtain the total mass and mass ratios. And if you could detect the peak frequency in massive neutron star oscillation phase, you can infer the mass, so you can infer the radius from the relation we found in this studies. Okay, let me discuss the electromagnetic counterpart. As I shortly touched in introduction, the ejected mass is important for the electromagnetic counterpart. This is the evolution of the ejected mass. And if the system is asymmetric, such as 1.2 and 1.5 solar mass, the ejected mass is greater than 10 to minus 3 solar mass. Based on the synchrotron radiation scenarios and our process element decaying scenarios, we can estimate flux, duration, and people velocities. So if the system has has asymmetric features, these events could be detected by the future programs.
So what are the kinetic energies that the ejector has?
This one, typically 10 to 50 hours. Kind of.
And how fast is the material moving?
Typical velocity is about 2.1, 20% of the speed of light.
So, so the most asymmetric mass ratio has the most ejecta, as you would expect.
Right.
And in terms of the equation of state, the softest equation of state, or the
In terms of the equation of state, the more soft equation of state produces a more mass ejected mass in binary neutron case. But in black hole neutron case, the relation is vice versa. I mean, soft equation of state produces not stiff equation of state produces most massive ejected mass by black hole neutron case. The last topic in binary neutron star merger case is a magnetic field. Up to now, the magnetic field is totally negative. The magnetic field could be amplified in binary neutron star merger. The possible amplification process is Kelvin-Helmholtz instabilities developed in the shear layers. When the two stars come into contact, and the other powerful amplification process is magnetic rotational instability inside a massive element neutron stars or accretion inside the accretion disk, which is formed after the collapse into the black hole. In both amplification process, a short wavelength model is essential. This means that you need massive power simulations. The typical grid resolutions in magnetized binary neutron star transfer is about 200 meters, but we estimated that the 100-meter resolution and long-term simulation for 100 milliseconds are required to figure out the magnetic field amplification.
So, well, that depends, of course, on the seed field that you have. What did you assume?
10 to 14.
10 to the 14?
Yeah.
Then I think you're off by 2 orders of magnitude in your non-scale estimate.
Yeah. But we assume the magnetic field is confined inside the neutron stars. And typical the magnetic field is estimated by the dipole field outside of the neutron stars. So, okay, we are planning to do a simulation, magnetized binary neutron simulations on K computers. And this simulation is one of program for the high performance computing infrastructure strategy program, and the full scale simulation will be done in these years. And by the way, this is a picture for the K computers, which has 80,000 nodes, and the peak performance is 10 petaflops. We have done a tuning of our code on these K computers. And this shows this is a scaling, which shows a good scaling up to the 80,000 cores with 50% efficiencies.
Sorry, so it's 80,000 nodes or 80,000 cores?
80,000. In full system, 80,000 nodes.
And so 8 times that many cores?
8 times, yeah. one node has eight cores.
So 160,000 cores. Okay, just one for a second.
Okay, in this figure, we start is 10,000 cores. So this is a very preliminary result, and this simulation is now running on the computers. And apart from the magnetic field, this simulation is the highest resolution simulation done so far. So gravitational waves is more accurate than the gravitational waves obtained so far. But this is a very preliminary, so I hope to introduce these results somewhere in the near future. Okay, let's move on to the black hole neutron star case. In black hole neutron star major case, is not as complicated as the binary neutron star case. The point is whether the tidal disruption does occur or not. If the tidal disruption occurs, the tidally disrupted neutron stars form an accretion disk around the black hole. Otherwise, the only black hole remains. The tidal disruption is imprinted in the gravitational waves as a sudden shutdown of the gravitational wave forms. And if it did not happen, the quasi-normal mode of the black hole can be seen in the gravitational wave forms. This is a schematic picture of the tidal disruptions. The fluid surface element as well as the neutron star itself are dragged by the black hole. And because of the finite size effect, there is a difference in acceleration between the surface fluid element and the surface fluid element at the center. This is a tidal force. If this inequality holds, the tidal force overcomes a neutron star gravities. We call the right-hand side quantity tidal radius. And if the tidal radius is greater than inner stable circular orbit, the tidal disruption occurs, otherwise it doesn't. Inner stable circular orbit is an orbit within it there is no stable circular orbit, which means that the fluid element inside the inner stable circular orbit cannot escape from the capture by the black hole. The key ingredient of the tidal disruption in black hole neutron star is in black hole neutron systems, mass ratios, compactness, and the black hole spin. Increasing the mass ratios and increasing the compactness, the system is less subject to the tidal disruptions because of the shrink of the tidal radius. On the other hand, if increasing the black hole spin enhances the chance of the tidal disruption because of the shrink of the inner stable circular radius. This is a schematic picture of the gravitational wave spectrum in black hole neutron star system. And the first case is a tidal disruption case, and the gravitational waves suddenly shut down. And this shutdown is printed as an exponential decay in the spectrum. And the second case is a no tidal disruption case. In this case, the gravitational waves is in this case, the quasi-normal mode is efficiently excited, and in Fourier space, there appears a hump as like a prompt black hole formation case of the binary neutron systems. The last one is a mixing case, and the spectrum of this case is shifted to the high frequency side compared to the case one because of the excitation of the quasi-normal mode. We explored the black hole neutron star simulations by performing the systematic study with finite zero temperature equation of state and the finite temperature equation of state separated. So today I would like to introduce the LIGO. So this is a result for the model in which the black hole has a spin 0.5 and the neutron star mass is a 1.35 solar mass with a Shen equation of state. And the left-hand side figure is the densities, and the right-hand side figure is an entropy.
What's the mass ratio?
Mass ratio is a 3.
Okay. So that's what we did with DUIS, right, in 2010.
Yeah. And as like the pioneer neutron star case, after starting the simulation, the separation between the two gradually decreases because of the radiation reaction. Then the neutron star is tidally disrupted, and this tidally disrupted neutron star forms an accretion disk around the black hole. And spiral arms develops, and matter is heated up by the spiral shocks. The typical density of the accretion disk is 10 to 12 or 10 to 13 gram per cubic centimeters, and the entropy is an order of 10 in Boltzmann. This is an accretion. This is an evolution of accretion disk mass for the spinning black hole case and the non-spinning black hole case. And you can see that the more massive disk is formed for the spinning black hole case. This is because the inner stable circular orbit radius in spinning black hole case is smaller than the non-spinning black hole case. If you fix the mass ratios and the neutron star structures, the separation between the tidal radius and the inner stable circular radius is larger for the spinning black hole case in comparison to the non-spinning black hole models. This means that the duration of the angular momentum transfer becomes long, so the fluid element gets a chance to escape the capture capture by the black hole. And this is why the spinning model, black hole model, produces a massive disk.
This is for prograde spin.
Yeah, that's
And
right.
if it was a,
If you assume that retrograde spin final mass is less than the non-spinning black hole. So the final system is a black hole surrounded by the massive disk and a hot disk. So this model could be a candidate of the central engine of gamma plus, short gamma plus. Okay, this is a gravitational-wave spectrum for the finite temperature models. In spinning black hole model case, the spectrum in spiral case goes up compared to the non-spinning black hole case, because the positive spin of the black hole makes the in-spiral phase longer due to the spin-orbit coupling. In the non-spinning black hole case, the quasi-normal mode is excited, and the spectrum is shifted to the high frequency side. The tidal disruption is characterized by the cut frequencies. And the right-hand side figure is a result by Kyoto et al. And in this figure, you can see that the cut frequency decreases. Cut frequency is shifted to the low frequency side with decreasing the compactness of the neutron source. And they provided a fitting formula for the cut frequency as a function of the compactness, and we confirmed that the finite temperature models is well fitted by these relations. So the strategy to construct the equation of state is very similar to the binary neutron star case, combining the information for the in-spiral waveforms and larger waveforms, and you can compare the compactness or neutron star radius from by using these relations. Okay. This is a neutrino luminosity curve for the spinning models and the non-spinning models. And the neutrino luminosity is enhanced after the mergers, which means that the neutrino is mainly emitted from the accretion formed by the tidal disruptions. The hierarchy of the neutrino luminosity amplitude is anti-electron neutrino, electron neutrino, and the others. And because accretion disk is quite hot, so the thermal photon produces positron and electron pair efficiently. In addition, the neutron star is mainly composed of the neutron, so this reaction proceeds more preferentially than these reactions and produces anti-electron neutrino efficiently.
And what is the typical energies for the spectrum?
20 in average energy.
And is there like a maximum, like it's not going to get above 50 MeV or so?
I didn't check the maximum. This is a physical quantities of the. This is a snapshot for the physical quantities of the accretion disk, and from these quantities we made it the viscous time scale, and this high amplitude neutrino luminosity is expected to continue at 100 milliseconds. So let me check the ejected mass in the black hole neutron star case. This is ejected mass, the function of time for the spinning models and non-spinning models, and typically 0.01 or 0.04 solar mass is ejected from the binary black hole neutron system. The typical velocity is 30% of the speed of light, and we can again infer if we can again estimate the flux and the duration and the luminosities in both scenarios. However, to make precise predictions, we should do nuclear synthesis calculations and photon radiation transfer. This is an ongoing project. Okay. I should stop here, or
No, you could, I mean, if you have more, we're curious to see more.
yeah,
Do you have time?
2 or 3.
Yeah, 10 minutes. Good.
10 minutes. Okay. Okay. Final topic is a black hole and a neutron star with magnetic field. And numerical simulation done so far suggested that in-spiral dynamics will be modified if you assume that max magnetic field greater than 10 to 70 Gauss, which is somewhat unrealistic part. The other point is starting the simulations in which the magnetic field is confined inside the neutron star, result in the toroidal magnetic field inside the accretion disk, which is formed by the tidal disruptions. This is a numerical relativity simulation by the Illinois group, and the color shows the density and the line shows the magnetic field lines. And the right-hand side figure is a contour plot with the fixed mescal fibers. So this system is expected to evolve like this if the MRI could be resolved in the simulations. This is a MRI wavelength. This is a MRI wavelength estimations with a hypothetical value of the toroidal magnetic field in with the current new setup of the with the current setup. This MRI wavelength is marginally too low. But as I mentioned in this slide, the strong toroidal magnetic field is unlikely to remain inside the torus. So they estimated the MRI wavelength divided by the grid resolution, which is about unities, even for the ultra-strong initial magnetic field. However, in this simulation, they use a gamma equal to equation of state, and if you change the equation of state, this result will change. Will change because accretion, this structure such as the density or the angular velocity strongly depend on the equation of neutron stars. And the other point is nested grid structure might be superior to the adaptive mesh refinement because in nested grid structure, the accretion disk is covered by the finest grid resolution or second finest grid finest grip. On the other hand, in the adaptive mesh refinement, the neutron star and black hole are covered by the finest grip box, and a cursor which will be assigned to the accretion disk. So it is difficult to resolve the MRI case. We are now exploring this point by performing the GR installations, and this is a result for the test calculations. And our result is qualitatively consistent with the previous ones. This is a magnetic field, a maximum magnetic field outside the black hole horizon, and toroidal magnetic field is indeed swallowed into the black hole at the time of absorptions. However, around the 50 millisecond, the toroidal field starts to grow exponentially, and we estimated the MRI length divided by the grid resolution, and which gives an order of is about 10. But this is a very, very, very preliminary result, so we should do a more precise analysis. So what do we have to do in black hole universe merger with magnetic field is to construct a self-conscious model which bridges this guy and this guy. And then we will discuss the magnetically driven window from the accretion system and discuss the central engine or shortcut first. Okay. I think I have run out of time. So this is a summary of my talk, and thank you for your attention.
Questions?
So I had one question in the neutron star mergers that led to the massive star ringing down. It looked like the F modes were ringing down in about 10 milliseconds, but there was then something continuing after that. Is that just numerical noise, or do you think it just like that one?
Sorry.
Yeah, like there.
In this case.
So there's a rapid decay from 10 to 15 milliseconds, and then there's something that continues
this
after
decay.
that. Yeah.
And this decay is mainly caused by the gravitational wave, because the gravitational wave carry away the angular momentum.
Right, but then what is it? There's a continuing oscillation after that. These small amplitude oscillations, and this is also because the massive neutron star doesn't have a perfectly asymmetric structures in final place. So So I think that's a sort of bar or something.
it emits a gravitational waves.
And it can last for how long? On the order of a second or even? Or more?
I'm not sure. I have never checked.
I mean, you always end 30 milliseconds after, so
Yeah.
you've never seen how far much. Okay.
Yeah.
So it doesn't look, I mean, it looks like it is damping out slowly.
Yeah.
I don't know.
But is it robust? I mean, once you have neutrino emission and all that, it may go down faster, no? Or
But the neutrino cooling time still is 1 second.
1 second.
Order of second. So it's a very, very long.
I have a question about the codes. I'm not sure I completely understand what you're able to do with these codes, but what if you considered a bigger black hole?
Sorry?
What if you considered a bigger black hole and a smaller neutron stars that you don't tidally disrupt? Is your code able to really detail the magnetic field threading of the black hole, that horizon, and any
Yeah.
kind of Faraday fluxes and electromagnetic radiation you might get just from the magnetosphere of the neutron star?
In this case, this is, sorry.
But that's still a small black hole.
Yeah. In this case, we fix the mass ratio is 0.3, so
But it's tidally disrupted.
that is disrupted.
Right, so if you make the black hole so big that you do not
okay.
tidally disrupt,
Okay.
but
But,
the
if you
neutron star
assume the
trans-
very high spin, so tidal disruption will occur even with very high mass ratio. By
eight solar masses? I mean, not for 10 or 12.
Okay, sorry. Okay. Wait a minute.
So if the black hole's just a 10 solar mass black hole,
Okay. Wait a minute. Sorry, this is but I think this is a prediction of this mask done by Francis Fugers, and this is something like this. Okay, this is the mass ratios of black hole, and this is the compactness of the neutron stars, and the color in the disk mask is 10% of the neutron stars. And if you assume the spin of 0.9, the tidal disruptions occur even for the mass ratio of 7.
Right, that's fine, but a lot of black holes very conceivably will have a higher mass ratio than that to a neutron star. So my question is just a simple one. Suppose you consider a 10, 12 solar mass black hole and a, typical mass for a neutron star. Would you be able to simulate the electromagnetic behavior of just the magnetosphere of the neutron star around the magnetic field when they're close enough that what you get is basically a threading of the black hole horizon? Is that something that you think you can follow in detail?
Yeah, but the high mass ratio is very tough to simulate in the calculations.
Sure.
So I think mass ratio 5 or 7 is feasible values.
I see. Okay, so that's just pushing the resolution of your grid
Yeah.
relative to gravitational wave stuff.
To follow up on this, you said your code for these results is ideal geometry.
Right.
Then you anyway wouldn't be able to follow the magnetosphere.
Okay, because it's ideal.
Since then you would need resistive effects. or
Well, you
force-free
definitely need the
properties.
Yeah.
resistive
Yeah.
effects.
Yeah, so he won't be able to do that with that super.
It just seems like there's this gap in what anybody can do with these codes.
Yeah, because you have different regimes. And
Right,
you have
nobody seems to be able to do the resistivity of the actual magnetospheric behavior like the synchrotron curvature.
They
Yeah.
put out something recently, right? But I'm not sure how.
Yeah, exactly.
Well, but even those, it's nothing physical, right?
Yeah, right.
It's not
Yeah.
on us,
I'm just saying this is at least-
micro.
That's right, it's just stuck
This is
in
the
by
only-
hand, they can't really
Yeah.
follow the synchrotron or curvature, radiation along the field lines, that sort of thing.
I had one more thing about the wavelength estimate for the MRI. You said for like a 10 to the 14 Gauss field that's completely confined inside.
This is not initial Breuer magnetic field, but magnetic field which is remained inside the accretion.
So you're saying a 10 to the 14 Gauss field inside the accretion disk.
Yeah.
Okay, so it's basically, so there was like another recent paper by Rizzola, by Rizzola's group, and they're saying something in it. This is a single hypermassive neutron star, and they say for like 5 times 10 to the 17 Gauss
Yeah, I know.
fields, they want at least 40-meter resolution. So I was wondering how the numbers fit together. That's just the different equation of state.
Okay, but compared to the hyperdimensional neutron star case, the density is fairly different. Okay?
Yeah, sure.
So the hyperdimensional neutron star in case the MRI wavelength is extremely short because
Right.
density-
Actually, I was more referring to your previous slide, the one that you had introduced before, where you were describing the ongoing simulation on the big supercomputer. Where you had this was, I'm not sure if this was binary neutron stars or neutron star black hole.
this case.
Yeah.
Yeah, so it is difficult to resolve the MRI in the hypermassive neutron star
Right.
case with this resolution. It is very different. But once the black hole is formed and the accretion is once this hypermassive neutron star collapses to a black hole and the accretion disk is formed, the condition to resolve the MRI becomes easy.
Yeah, sure, I agree on that. I think I misunderstood what you wanted to do. Okay, thanks.
So I have a basic question. I'm not anywhere in this field of neutron stars, but I think I remember you saying that to track the microphysics, use some truncation scheme, right? So for the correlation predictions. So how do you know how the results depend on different truncation schemes? Because the truncation, as far as I remember, kinetic theory is completely arbitrary.
I'm not sure, but my collaborator Yuichiro now trying to implement this formalism to the binary neutron star. So I think if he finished to implementation, we can compare the results. That's a future task.
Okay, thanks.
Okay, let's thank Kenta again. And refreshments next door.